wonder when you'll be able to hear. All right, let's get going, people. Predicting ions is a way to go. Okay, so general rule. What you probably learned once upon a time, the octet rule. Everything wants to have full S and P subshells. This gives us the noble octet or stable octet, what you probably learned about once upon a time. 2 s electrons, 6 p electrons gives you 8 electrons. This works great when we're looking at the nonmetals. Not so much for anything else. So the best rule is that everyone wants to be a pretty princess. Everyone wants to be noble. Everyone wants to look like the nearest noble gas. Now note, I said the nearest noble gas, not the next noble gas. For the metals, the nearest noble gas is the previous noble gas. For the nonmetals, the nearest noble gas is the next noble gas. So the nonmetals are very predictable, very regular when it comes to forming ions. The nonmetals all want to gain electrons, high electronegativity, they want to gain electrons so that they can look like the next noble gas. So the halogens right here, they're all one step away. They all have an almost completely full p subshell. So they just gain 1 electron, boop, and they're happy. So that gives them a -1 charge on their ions. The oxygen group, they're 2 steps away from the nearest noble gas, so they get a -2 charge. They gain 2 electrons, -2 charge. The nitrogen group, they gain 3 electrons to look like the next noble gas, -3 charge. Carbon, if you can induce it to do so, carbon will gain 4 electrons, but that's a lot. Okay, carbon is a tiny little atom cramming 4 electrons in there. That's, whoo boy, that is asking a lot. Okay, so the nonmetals want to gain electrons. The metals want to lose electrons. So losers on the left, gainers on the right. I am sorry, I was not able to come up with a good bit of alliteration for the nonmetals. Okay. But this is the general trend of what we're looking for. So the other nonmetals that are easy to predict are over here in the S block. Okay. Again, because of that nice octet rule. They are going to lose their s electrons and look like the previous noble gas. Okay. So the first column, they only have that 1 valence electron. They lose that, they get a 1+ charge. So lithium loses 1 electron to get the same electron configuration as helium. Potassium loses 1 electron to get the same electron configuration as argon. Okay. Now the alkaline earth metals, the second column, they have 2 electrons. They lose both of those, and they end up with a +2 charge. So that is most of, not all of, but most of the easiest ions. Okay. These, they'll definitely expect you to know. They'll expect you to remember, to be able to work with these, to predict what charge these ions will have. Okay. So the alkaline earth, so the alkaline metals, the first column, they get a 1+ charge. The alkaline earth metals, number 2, they get a 2+ charge. Then there are 3 atoms, 3 elements in the middle of the periodic table. Now, most of the D block and P block, those metals can make multiple ions, but not these 3. Okay. These 3 metals can only form one kind of ion, and that's silver, zinc, and aluminum. Okay, I call it the staircase because they make a little staircase right here in the middle of the periodic table. 1+, 2+, 3+. Silver, zinc, aluminum. Climb the staircase, the charge goes up. Okay, silver, zinc, and aluminum, 1+, 2+, 3+. You absolutely must remember those because it's not going to be super obvious that that's what's going to happen. Because, like I said, they're in the middle of the periodic table. D block and P block are a little bit harder to predict. Not these 3: silver, zinc, aluminum. 1+, 2+, 3+. And then, of course, the nonmetals, the anions, those are all super easy. Just how far are they from the nearest, from the noble gas, right? Halogens is -1, chalcogens is -2, nitrogens is -3, and then carbon by itself is -4. So, metals, 2 columns are easy. The S block, nice and easy, 1+ and 2+, and then you have the staircase, 1, 2, 3. The nonmetals are also easy. They just form anions, -1, -2, -3, -4. Okay? It's all just based on how far they are from the nearest noble gas. The rest of the metals get a little bit more difficult, and I'm not sure how much they're going to expect from you. So next up, we have the medium ions, the p-block metals, or post-transition metals. Okay? So when we hop over to the periodic table, the p-block metals are these guys right here, highlighted in blue. Okay? Ignore aluminum and polonium for the moment. Aluminum, because it is that 3+, and we don't really have to worry about that. Polonium, because we're never going to deal with that. It's just not going to come up. So we're going to be dealing with gallium, indium, and thallium. So let me see, clicking on that. Well, okay. Boop. Nope, doesn't. Okay. So gallium, indium, and thallium here in group 13. Tin and lead in group 14. And then bismuth all by its lonesome here in group 15. Now, I call these the medium ions because they're fairly easy to predict. It requires a little bit more effort. You can't just count your way to the nearest noble gas, but they're not that difficult. Okay, so gallium, indium, and thallium comes up first. Then we have tin and lead. Then we have bismuth. We consider them as groups because electron configurations. They all have very similar electron configurations. They all have the same kinds of valence electrons. Gallium, indium, and thallium, they all have 2 s electrons and 1 p electron. They also all have full d shells. Okay. Thallium, by the time you get there, it also has a full F shell. You can see that with the 32 there on the left. But that doesn't really matter. What matters is the valence, 2s and 1p. Meanwhile, tin and lead, again, they have full D shell for tin, a full D, and a full F for lead. But what really matters is they have 2s and 2p electrons in their valence shell. Bismuth, meanwhile, has 2s electrons and 3p electrons. The reason that's important is because of the way these post-transition metals form ions. What happened to the thing? Where's my... There it is. All right. The way they do that is by losing some electrons before they lose other electrons. So the p-block metals lose their p electrons, then they lose their s electrons. Okay? Regardless of how many of each they have, they lose all their p electrons to form their first ion. Then they lose their s electrons to form their second ion. Okay? So first they lose their p, and then they lose their s, so that by the time they're done, they'll have lost all of them. Okay? So we look at gallium, indium, and thallium. First up, 1 p electron, 2 s electrons. So the first thing they're going to do, they're going to lose their p electrons, and they'll end up with a 1+ ion. Okay, so gallium, neutral, starts off with argon, 4s2, 3d10, 4p1. Then it loses that p electron and becomes gallium 1+, argon, 4s2, 3d10. This is an example of the electron configuration of an ion. They will expect you to be able to do this, to find the configuration of an ion that has lost some or all of its electrons, or if you're looking at an anion that has gained some electrons. Okay, so gallium 1+, it lost that p electron. And then gallium goes on to lose those s electrons to become gallium 3+, leaving it with argon 3d10. Okay. Those d electrons aren't going anywhere. Completely full D subshell, degeneracy all over the place, they're not going anywhere. Honorary core. Next up, we have tin and lead. So they each have 2 s electrons and 2 p electrons. So for tin, first it's going to lose those p electrons to become tin 2+. So it goes from krypton 5s2, 4d10, 5p2 to just krypton 5s2, 4d10. To form the other ion, it loses its s electrons also, making it 10 4+, krypton 4d10. Lead does the same thing, except it also has f electrons that aren't going to get touched. And it's going to be losing from the 6th energy level, so it's going to lose 6p2 and 6s2, but it's going to do the same thing to make lead 2+ and lead 4+. Then we have bismuth all by himself. Xenon, 6s2, 4f14, 5d10, 6p3. Remember the f and the d electrons? Not going anywhere. So the first thing bismuth is going to do is it's going to lose those p electrons, become bismuth 3+. xenon 6s2 4f14 5d10. And then you induce it to lose some more electrons. It becomes bismuth 5 plus, xenon 4f14 5d10. So like I said, I call these the medium ions because you can get multiple possibilities. You're not going to be able to predict which way it would go if they asked you which ion it would form, but you know that they're going to form two ions. You know what those two ions are going to be, and you know the electron configurations for each of those ions. Okay? If they ask you for the electron configuration of any of these half dozen ions, or well, technically 12 ions, you'll know what those electron configurations are. First, they lose their p electrons, then they lose their s electrons. All the p, then all the s. I know you hate your cone of shame, buddy, but it's going to have to stay on until your chin is better. All right, next up we have difficult ions. The transition metals, the D block metals. These are difficult because they don't just go with 2 ions. Some make 3 or 4. Some only make 1, like silver and zinc. They're kind of wild. They are very difficult to predict. Some of them are easier than others, but you'll not be able to predict them just by looking at them. So you will not be asked to predict it. However, they could also ask you to explain why it forms this ion by asking you for the electron configuration of a D block metal, of the ion of a D block metal. Now, D block metals are kind of backwards from the P block. Okay? So the transition metals are different from the post-transition metals. Okay? Where the P block metals lose P, then S, the D block metals lose S, and then D. Okay? And they don't necessarily lose all of their D electrons. Okay? They can lose some of them, or they can lose all of them. Okay? They can go anywhere in between. Okay? So they're like those. That's why they're a little bit harder to predict. Okay? So remember, P block metals, P then S, D block metals, S, and then D. So here we have one of the easier ones, iron, right there in the middle of the periodic table. Element number 26. It is argon 4s2 3d6. The reason it's simple is because it only forms 2 ions, and those ions are fairly easy to understand. Okay? So first, it's going to lose both of its s electrons to give it a 2 plus ion. So iron 2 plus is argon 3d6. Some of you may have already leapt ahead to understand what's going to happen next. It's going to lose one and only one of its d electrons. That leaves it with a half-full d subshell. That makes it very, very happy, and a 3 plus charge. So iron 3 plus, argon 3d5. So iron 3 plus is a very, very common ion for iron. Iron is much, much happier as iron 3 plus than it is as iron 2 plus. Iron 2 plus is possible. You can do that. But iron 3 plus is more common. This also explains, for example, silver. Silver is one of those anomalous electron configurations that you absolutely had to have memorized for the last test. Silver was krypton 5s1 4d10. Remember, it bumped an electron out of the s block into the d block to give it that full d subshell. Thus, when it loses its s electrons, it just loses the single s electron to become silver 1 plus, argon 4d10. And then it's not going to touch those d electrons. Degeneracy all over the place. They're entirely happy. They're not going to go anywhere. Okay? For the same reason, we can understand zinc. Okay, let's pop back over to the periodic table. Here we have zinc. And zinc is abbreviated electron configuration. Argon. Is it argon? Yes, it's argon. 4s2 3d10. So zinc is really, happy to stop with zinc 2 plus to become argon 3d10. It has no particular motivation to lay a finger on those d electrons. So it's just going to stop at zinc 2 plus. Now, the reason we only focus on zinc, we don't talk about cadmium and mercury, is because at the higher energy levels, the heavier elements, because the energy levels and sublevels are starting to get closer together, you start to get some complicated, weird sorts of behaviors. So we want to stress these simpler ones that you can definitely memorize. In this case, silver, zinc, aluminum. 1 plus, 2 plus, 3 plus. Along with, of course, the S block metals and the nonmetals. Okay, let's go back to the slides. All right, so what are they going to expect you to know? They're definitely going to expect you to know the simple, the easy ions, the easy cations, and the nonmetals. Okay, so the S block metals and the staircase, as well as the nonmetals. Okay, 1 plus, 2 plus for the alkali and alkaline earth metals, 1 plus, 2 plus, 3 plus for the staircase, and then the nonmetals, -1, -2, -3, -4. Okay. They're also going to expect you to know how to find the electron configuration of a given ion, whether easy or harder. Okay, for the anions, that's easy. You're just going to shove electrons into the empty sublevel until it's full. So for the nonmetals, you're just filling up the p block until you get to the full p subshell. For cations, you're removing whichever electrons you're supposed to remove. For the S block metals, you're removing S electrons. For P block metals, you remove P, then S. For D block metals, you remove S and then D. It's a little bit more memorization, but I'm sure you can handle that. There's not a whole lot there. Okay? But that's what they're definitely going to expect you to know. They're going to expect you to have memorized the easy ions. They will expect you to know those numbers, to know what ions those elements form, because they're only forming the one ion, very easy to predict. Therefore, you should be able to predict those. Okay? They won't expect you to predict what ions are going to be formed by the medium or the hard, by the P block metals or the D block metals, okay? With the exception of the staircase. Okay? But they will expect you to be able to do the electron configurations for those. Okay? All right, so with that, we are done with this set of slides. And I have been talking pretty much nonstop for an hour and a half. I'm feeling a little bit raw. I'm going to go ahead and call it a night. I will finish these lectures tomorrow evening after my D&D game. And with that, I will call it an evening.